Hello my dears, today we will start module number 3, where in this module we are going to study the steady state error and transient response. In this material we will study with the steady state error for Unity Feedbak. In the delivery plan of this module, we are going to cover it in 3 weeks as usual, where we are going to cover the steady state error for Unity Feedbak and the steady state error for a system with disturbance. Then we will start in the transient response. Let us start with the steady state error. Before we go through the steady state error, let us know here that there are 3 types of inputs will be sent to any control system for testing. They are the step response, the ramp, and the parabolic. So any control system will be tested against these inputs. In Laplace, their expression for step it's 1 over s, or the number of step over s. Then for ramp, it's 1 over s squared, and for parabolic, 1 over s cubed. Once again, input signal can be step, ramp, or parabolic, where the step is a step input useful in determining the ability of control system to position itself with respect to stationary. I mean, if the system required to position itself with respect to stationary, we are assuming this is stationary, so we need the new position. The new position is going to be this. That's what we mean by a step input. So for that kind of system, step input is used for testing. For the ramp input, used to test the system ability to follow linearly increasing input, or tracking a constant velocity target. So when the input is linearly increasing, or when the output required to be linearly increasing, we can use ramp input, so linearly increasing. Again, when the output is linearly increasing, we need an input of linearly increasing to test it, which is going to be the ramp input. The parabolic input used to represent acceleration target. So it's as simple as this. Whenever we have some target with acceleration, we are going to put the input as parabolic. So when the output is accelerating, the input is supposed to be parabolic input. The representation of the steady state error for the step input, if I want to discuss it here, we discussed this one before, but let us discuss it one more time very fast. For the step response, we are having here 2 outputs. If I look at output number 1, we found that the input is a step. The input is a step, which is this one. And the output start increasing. Output start increasing until at certain point it match with the input. For this kind of system, we used to say the system got no steady state error because the input and output are equal. This is the input and this is the output. So input and output are equal at the steady state. So the steady state error equal to 0. To understand it better, let's go to number 2, to output number 2. In case of output number 2, we'll find that the system is increasing, I mean the response increasing until it reaches steady state. But when it reached to the steady state, we found that it's far from the input. So we used to call this one system is stable, it's fine, but it's having its steady state error equal to E2. I mean there is a steady state error. Steady state error by definition is the difference between the input and the output. So if this is the input and this is the output, this is going to be the steady state error. That's how we can look at it in terms of step input. How about if ramp input? If ramp input, let us assume that this is the ramp, and we will compare how the output is going to look like. I will take output number 1. In output number 1, we will find that the response is increasing until finally it matches with the input. At that time, we used to say it's having no error. Steady state error is equal to 0. Why it's 0? Because at the steady state here, at this stage till infinity, we found that the input and output are equal. To get it better, let us go to input number 2. In input number 2, we found that the response is increasing, and when it reached the steady state, we found that there is difference between the input and the output. So the difference between the input and the output is known as the steady state error. Let us check output number 3. What is output number 3? In output number 3 here, he's putting a case to make us clearer about stable or not stable system. The response is increasing, and how am I reaching a steady state in the previous two systems? When the distance between the input and the output fixed. I mean, it's the same distance, the same steady state error. When I look at number 3, I found that the distance between the input and the output is keep increasing, which means signal number 3, the system is not stable. So he's saying here infinite steady state error. So steady state error is going toward infinity, because as we are going, or when I look at this axis, the time, as the time axis approaching infinity, you will find that the distance between this point and this point equal to infinity. So that's called the system is not stable. So of course we don't expect this one. We don't expect this one from the control system. In control system, we are expecting output number 1 and output number 2, whether here or here. Steady state error by definition is equal to the input minus the output, or we can express it as Rs minus Cs, where Rs is the input signal, Cs is the output signal, whether the system is having this representation, I mean general representation, or we are having unity feedback system. We are going to discuss this one and this one in separate way. But whether it's again this one, this system general representation, or the unity feedback, both of them, the error will be this signal minus this signal. That's why here, this not minus this signal. It's minus this signal because this is the output. So how to represent the error? We are getting this plus, this is minus. That means whatever signal coming from here minus the signal coming from here will produce the error. How about for the other style? The other style, look here. This is the input, this is the output. Output is fed back to get Rs minus Cs, which equal to Es. So this is the error here, this is the error, and in this case, this is the error. Let us see how we are going to analyze the steady state error for these kind of systems. Before we proceed, we need to know what is the source of a steady state error. So here he's saying the source of a steady state error, or why do we have a steady state error in our system? There are two reasons for that. He said here, due to nonlinear source. Example is the backlash of the gear. So there is the system by itself, its mechanism is causing this steady state error. One of the example is the backlash of the gear, which the gap between this gear and this gear, it's going to have gap, which I am shading it now. So that one is causing kind of error or steady state error in the overall system. Or sometimes from the configuration of control system. In the control system, with the block after block, we may get the steady state error due to the travel of signal from block to the other block. In our discussion here, we are not going to study this. We are going to study only the error due to control system problem. We will study the steady state error due to control system. In the steady state error analysis, we are going to discuss the system which expressed in two different ways. If the open loop transfer function given, that's going to be discussed after a while. And here we are going to start if the closed loop transfer function given. What does it mean? If I have the system, let's say this is the system with input and output, and we have the transfer function here given. If the system is like this, how am I going to deal with it? So we are going to call it, in this case, we are going to call it T of S. So if T of S given, it's going to be discussed as seen here. Here is T of S, here is the input, and here is the output. So to analyze the steady state error, we are going to evaluate it this way. But I want you to catch the point of the given transfer function. It's the closed loop transfer function, means the system is having input, output, and transfer function. If we derive the equation for the calculation of a steady state error, it's very simple here. ES equal to RS minus CS. Then we will evaluate CS here, CS equal to RS, because RS is coming here multiplied into TS. Rearrange the equation, we are going to get ES equal to this value. Now ES equal to RS into 1 minus TS. This is the error at certain point, but because we want to make sure of the error, we are going to evaluate it at infinity. What do I mean here? I mean, let us say this is the response, this is the input, and the output is going to be this one. Let's say this is the output. So if you notice here, the distance between the input and output, I'm talking about this distance, keep changing. When it's going to get to the steady state, we are not sure. That's why we are going to calculate the value at infinity. Means what will happen at infinity. To do this, we are going to evaluate the final value theorem, or we are going to apply the final value theorem, where the final value theorem saying if the function, we want to evaluate the function at infinity, we are going to find its limit as t approaching infinity. Or if the function in S domain, I mean we have the Laplace, we will find the limit as S approaching 0 for S into the function in Laplace. That's the point. So this is our method. This is what we are going to apply. We are going to apply this one because we are dealing with function in Laplace. So if we apply it, we will find that the error is to be calculated as the limit of S into RS, which is the input, into 1 minus TS, where TS is the closed loop transfer function of the system. Here is example on that point. We are having a system with a closed loop transfer function, TS. We used to call it TS. Means we are having, this is the system, this is the input, this is the output. Our system looks like this. So if this is the transfer function here, what he wants us to calculate the steady state error. If the input is unit step, this is the equation. So it's the limit of S into RS into 1 minus TS. Let us substitute. It's going to be S into 1 over S, which the input RS is 1 over S, 1 unit step, into 1 minus the TS, which is the transfer function, which is this one. So we will evaluate it. When we evaluate it, we will find that the limit is equal to 0.5. The limit means the error, the steady state error at infinity equal to 0.5. Now in terms of GS and the system is unity feedback, what does it mean here? It means what I have about the system, what information I have about the system is GS. But GS is placed in a control system with unity feedback, as you see here. So the error is going to be this one, this value. If the case is like this, how am I going to evaluate it? We are going to evaluate it by calculating ES. I mean the equation for ES. So we will develop it similar to what we did in the previous case, or in what we have done in the closed loop system, which discussed in the first module. ES equal to RS minus CS, as you see here, ES equal to RS minus CS. Then CS equal to E into G, CS, which is this value, this point here, this point CS, equal to ES into GS. Now from these two equations, we can find ES equal to R minus ESGS. Rearrange the equation for ES, you will find that ES equal to this value. Again, this ES is calculating the value at certain point, which we are not clear whether we are reaching the steady state or not at that value. That's why we will calculate the error at infinity. To calculate the error at infinity, we will apply the final value theorem, similar to what we did in the previous case. So here is the final value theorem. When we apply it, we will find that it's the limit as S approaching 0 for S into the equation found earlier. So when we substitute ES as shown here, you will find it's the limit of S into RS over 1 plus GS. So that's how we can evaluate the steady state error. And this formula is general. Now let us assume cases. Assume cases for each input, we are going to develop the steady state error. What I mean by this, for each input type, we have three types of input mentioned earlier at the beginning: step, ramp, and parabolic. Step input, ramp input, and parabolic input. For each input, we will apply it in this formula, and we will see how the formula going to look like after that. We will start by step. If the input is a step, of course, we will consider 1 unit. So 1 unit step to see what will happen. If I substitute Rs as 1 over S, as you see here, this S will cancel this S. What will remain is this. So that means the error is equal to the limit of 1 over GS. To apply the limit to this function, it's going to affect only GS. That's why we can write it in this format. So we will find that ES equal to E of infinity, means the error at infinity, equal to 1 over 1 plus the limit of GS. Remember this GS, to remind you again, if the open loop transfer function given. So here is GS. So if this is given, we can apply this formula, especially if the input is RS. If the input is RS, we can apply this formula. Now, what I want from the error, how I want the error to look like. Do I want the error to be certain value, or I want the error to be 0? Let us look or consider this point. He said here, if you want the error to be 0, if you want the result of the previous equation to be 0, remember, it's E of infinity equal to 1 over 1 plus the limit of GS. If I want this value here to be 0, what should I do? I have to make the limit of GS equal to infinity. So we are going to get 1 divided by 1 plus infinity is equal to 1 over infinity. 1 over infinity is equal to 0. That's how I can get E of infinity equal to 0. So again, to get this value equal to 0, we need this value to be infinity. Okay, let us replace this GS by the function by itself. So we will assume in general the format of GS going to be like this: something in the numerator divided by the denominator. I will consider S to the power n because it's our target. Here, S to the power n. So if the value of n, equal to 1 or more, what does it mean? That means the limit of, if there is S here, we are going to get the value as the limit of something over S into whatever bracket. So this is going to give me 0 in the denominator. That means the limit of this limit will be equal to infinity by the end of the day. That means this value equal to infinity, which result in E equal to 0. He wanted to say that we must have one S at least in the denominator, one S at least in the denominator. This is going to result in the error equal to infinity. That's the idea. What is the meaning of one S in the denominator? Means 1 over S. So in the transfer function, we must get 1 over S, which is known as integrator. So in any transfer function, if I have integrator and we calculate the steady state error with step input, we are going to get the steady state error equal to 0. Even without calculation, you can finalize it, or you can decide that it's equal to 0. Notice here that the integrator, which we talk about, it's the 1 over S, means the value of S equal to 0. I mean, it's looking, obtained or found at the origin. How about if the value of S is equal, the power of S equal to 0? Means we see what we found in the previous slide, S to the power n. We said n must be equal to 1 or more. What if n equal to 0? If n equal to 0, that means we will have no S here. No S will be available. It's going to be equal to 1. Same as the case here. So in that case, you will find that the limit going to give you certain value, which will end up with the error equal to finite value. So now I come out with conclusion. If there is, for that case only, for this case, when the input is a step when the input is a step. If there is integrator, the error will be 0. If there is no any integrator, the error will be finite value, certain constant, certain value. I hope whatever I discussed earlier is clear. This is going to make this point also clear. If r of s equal to 1 over s squared, that means the input is ramp. Let us substitute it. So if here r equal to 1 over s squared, 1s will cancel this s. I will get by the end 1 over s. So if this s cancel one of the s, there will be one s remaining. That s, if I rearrange it in the equation, I will find that it can be written as instead of 1 over s over this denominator, we can write it as a 1 over s into the denominator. So I'm going to have s here and s here. So now it's equal to 1 over s plus s into gs. When we apply the limit, you will find that this s will always give me 0. So it's not going to be there, which means we are going to find the limit of 1 over s into gs, which can be written as you see here. So it's going to be the error if the input is ramp equal to 1 over s into gs. I mean the limit of s into gs. That's good. So when am I going to get the error equal to 0? How to get the error equal to 0? It's going to be when the denominator here equal to infinity. Notice that the denominator there is s. Now how to make it equal to infinity? Because gs by itself has numerator and denominator. This is gs. So there will be s multiplied into this function. Now if I have here only one s, this s will cancel this s. The remaining will be finite value. That means if I want the error to be 0, I have to get this value to be infinity. How to make it infinity? We will have s equal to n equal to 2 or more. N equal to 2 or more. What is the meaning of that? If n equal to 2, that means, let me put small example here for you to catch what I mean. If let us say the g of s equal to 1 over s plus 1. Let's say like this. If I want to calculate the error for this one, it's going to be the limit, or s into s plus 1. S into s plus 1. I'm going to find it as a 1 over the limit of s into 1 over s plus 1. The limit of s in, yes, like this. So it's going to be 1 over the limit of s into 1 over s plus 1. As you see here, the limit of 1 over s into gs, where gs is equal to 1 over s into s plus 1. So in this case, this s will cancel this s. When I calculate the limit for this one, I will find that the limit is equal to 1. So finally the value equal to 1. How am I going to make this value equal to 0? To make it 0, I have to have here s square. So if I make it s square, this s will cancel one of the s's there. So the remaining will be 1s. So it's going to be the limit of 1 over s into s plus 1. Since I have s here, it's going to give 0 in the denominator. The 0 in the denominator gives me the answer of infinity. That means the limit all will be equal to infinity, which means 1 over infinity will give me 0 at that time. That's what he means. So here, if you notice this system, we have one integrator, but one integrator will give me finite value. Two integrator means s square will give me 0 error. So that's the idea. So there must be minimum 2 pure integrator in the system, in the open loop transfer function, to get the error equal to 0 if the input is ramp. To get the error equal to 0 if the input is ramp function, as you see here. So here he's giving us the the finite, how to get finite. If we have one integrator, it's going to give us finite value. So again, if I want to get the error finite value, or if the error comes as a finite value, that means we are having at least one integrator in the denominator, in the transfer function. If there is one integrator, that means the error will be finite value. Now, how about if we have no integrator? If the system got no integrator, that's how it's going to look like. S into GS will be equal, no integrator if you notice, no integrator. So when I want to apply the limit to this function, or if I want to calculate the limit of this function, we have S here. S is equal to 0. That means all this function will be equal to 0. So I'm going to get here the limit of S into GS equal to 0, which means the error is equal to 1 over, this is all 0, as I mentioned just now, which equal to infinity. Now I come out with conclusion. I can say here, for ramp input, if there is no integrator, we will get the error equal to infinity. If there is one integrator, I mean in the closed loop, open loop transfer function, if there is one integrator, we are going to get finite error, means certain value. If two integrator or more, we will get error equal to 0, or we will get the error equal to 0. In case of parabolic input, which means when R is equal to 1 over S to the power 3, same exactly as before, same style, same way of thinking, we are going to end up with the error is equal to 1 over the limit of S squared into GS. Which very clear that if I want the steady state to be 0, if I want the steady state error to be 0, if I want this value to be 0, we have to make this value equal to infinity. How to make the value equal to infinity? We must get n equal to or more than 3. I mean n, this n supposed to be equal to 3 or more than 3. Okay, and following the same style as before. If more than 3 or equal to 3 is going to be 0 error. If equal to 2, it's going to give me finite error. If less than 2, it gives me infinite error.